Let's continue with optimization in section 5.4. Pause the video and take a look at Neuhauser 5.4 number 24. It gets into some basic stuff about alleles and genetics. They mention probabilities and such. You don't need to know that for the sake of doing the math of the problem, but you do need to understand it for the context of understanding what this problem really solves. So anyway, once you read all of that, you'll get to the part where they say that W bar equals P squared times W11 minus 2W12 plus W22 plus 2P times W12 minus W22 plus W22. Okay? That's one of the things they make you show, given that, Q equals 1 minus P, and you simplify, blah, blah, blah. This is what you wind up getting for the function that, by the way, is the average population fitness for a population, a set of things, or whatever, is given by this function right here, okay? So they give us a couple of situations. I forget what the third one is, so I'll just do the first two. The first situation is where you have that W11 is equal to 1, W12 is equal to 0.7, and W22 is equal to 0.3. And then the second situation, I think it's called directional something. I forget what it is. The second case, W11 equals 0.7, W12 equals 1, W22 remains at 0.3. And that's called, I think, overcorrected or overpopulation, something with over. The other one is under something. I forget what the other one is, so I'm just going to put a question mark. You can look it up, and you should try it. But you should be able to do that after we do the first two parts. So what we're going to do is we want to find the values of P that maximize W bar. So we take the derivative, set it equal to 0. So we just do that, right? Now the book refers to this as dW bar over dP. You could also call it, W bar prime of P if you wanted, right? Anyway, you get that this equals, now remember that P is the variable. P is the variable that, by the way, is always between 0 and 1. Just keep that in mind, because P is a probability. And anyway, the W11, W12, W22, they're all constants, so you just get 2P times these constants plus 2 times these constants. And then that last constant goes away, right, when you take the derivative. And you set this equal to 0. And then when you wind up solving for P, you get that P equals W22 minus W12 all over W11 minus 2W12 plus W22. Okay? And then we just try it for various, for the cases 1, 2, and you'll try it for 3. Okay? So for case 1, we have that P is going to equal, W2, so I think it's going to be 0.3 minus 0.7 all over 1 minus 2 times 0.7 plus 0.3, and that winds up equaling negative 0.4 over negative 0.1, which equals 4. And if you note that P is supposed to be between 0 and 1, that just doesn't make any sense. P is a probability. So that's not a thing, right? So instead what we do is we also test our endpoints, right? We say, okay, W bar of 0 is, right, because remember, we're trying to find the values of P that maximize W bar. We have this value that's just not working out, right? So we go to the endpoints, 0 and 1. W bar of 0, I think you'll see that this will go to 0, this will go to 0, right, because we have P equals 0. And so you're just left with W22, which is 0.3. And W bar of 1 is going to equal, let's maybe put that close together. What is W1 going to equal? W bar of 1. Well, if you do it out, I believe you wind up, right, the P's just kind of go away, and you're left with, let's see, W11 remains untouched, so that's just 1. Minus 2W12 is going to cancel with the plus 2W12, so that goes to 0. W22 minus 2W22 plus W22 also cancels out, and you're left with 1. So W bar is, so I guess you could say W bar of 1, I guess I'll just write it like this, is the absolute maximum fitness, right? And it occurs at P equals 1. All right, anyway, number 2. Actually, before I do number 2, just to show you really quickly, that's true, right? If we just take a look, right, we see that we do have, in fact, a local maximum at 4, but that doesn't make any sense, so we just take a look at our constraints, and we say, oh, not our constraint, but our interval for the values of P, and we say, oh, yeah, W bar of 1 equals 1. Anyway, let's see what happens when we switch up the function, when we switch up the values, right? For part 2, we have W11 equals 0.7, W12 equals 1, W22 equals 0.3. And so we're going to get P equals, still it's 0.3 minus 1, all over 0.7 plus 2 times 1 plus, minus 2 times 1. Plus 0.3. And this winds up being minus 0.7 over minus 1, which is 0.7. And that's kind of cool, because that means we do actually have a local max, potentially, or a local min, I suppose. But let's do it out, right? If we take a look at the interval chart, before and after 0.7, right? If we plug a value, like let's plug in 0 in for P into this function, you'll see that this goes to 0. And we're just left with 2 times W12 minus W22, which is positive. So we do, in fact, have a positive derivative before 0.7. And if you plug in a value like 1, for example, you'll just see that it winds up being negative. So I'll just say, so W bar of 0.7, which equals, what does that equal? I don't even know what that equals. It's something terrible. Let's see if we can solve it real quick. It's 0.49 times, this is going to be negative 1 plus 1.4 times 0.7 plus 0.3. We wind up getting negative 0.49. What's 1.4 times 0.7 plus 0.98 plus 0.3? Is that going to be 128 minus 78 point? I think it's 0.79 is what I'm getting. I might be wrong about that, but I think that's right. I believe I am getting 0.79. Correct me if I'm wrong. So global or absolute maximum, right? That occurs, just to be crystal clear, at P equals 0.7, all right? And that's what we've got.